Hello guys, in this video we are going to see some iterative estimation methods. So in particular we are going to see the Gauss-Newton method, the Newton's method and the gradient descent method. Okay, so let's start with the Gauss-Newton's method. So say we are given with a equation like this, say x is equal to some f of p, where f is any function over here. This can be any general function, but it is a vector valued function. So here you can see that this p is nothing but a vector. So it is m dimensional parameter vector, which one can say, and x is an n dimensional vector. So this f over here is a vector valued function. It takes input as a vector and it has an output also as a vector. Okay, so we have seen a general case. So if your f of p is a linear function, so that can be denoted in matrix notation like this. So where a is some matrix and p is the parameter vectors. So we have seen this a lot of times throughout this series. So you can always solve that with a linear least squares problem. But if your function is not linear, if it is quadratic or something else, polynomial or something else, then you will not be able to solve it with the least squares approach. So now we are going to see a general method or a iterative method by which you can solve any function f. Okay, so we just model this equation like this. So it is not very easy to get the exact value of p. So what we say is we are going to find an estimate value of p, naming it as p cap, which will have some error. So this might not be exactly equal, but it will have very less error. So that is what we want some p cap which will be a small approximate of this p, actual p, but it will have very less error. So this e over here or epsilon over here is the error that we have to minimize. So we have to minimize the error. That's the motto. Okay, to solve the case where f is not a linear function, we may start with an initial estimated value p naught and then proceed to refine the estimate under the assumption that the function f is locally linear. So what we do is we assume any initial estimate. This could be random or this could be some good guess that one can have. So this p naught, say if this is my function, the f, this function f is something like this, suppose. So if we start with a p naught somewhere over here, then what we have to do is we have to go in that direction where my error is reduced. So given a p naught, now I have to add some del quantity step by step. So step by step I will add some del quantity so that I reach the minimum. So that is the approach of mostly all the iterative methods. So given some p naught, in which direction should I go to update this p naught such that my new error is minimum? So I have to find del such that the new error that I have got, say epsilon 1, is less than the previous error epsilon naught. So that is my task now. So whenever you get this notation, you always call for the Taylor series for your help. So we have our Taylor series which says f of p naught plus delta is equal to f of p naught plus j delta. So where j is known as a Jacobian matrix. So let us just see this in a little detail so that we understand what this Jacobian is. Okay, so let us just start with a simple scalar function. So say f is a scalar function, uh, and it has the parameter, it has an input x naught. Okay, so f of x naught plus del x. So it is the same case as we saw over here. There is some initial estimate p naught and you are trying to add something into it. Similarly, there is an initial estimate x naught and you are trying to add del x into it. So this can be approximated by Taylor series like this: f of x naught plus del f by del x at x is equal to x naught into del x, and there will be some other higher order terms. So if we just ignore those, then you can have this kind of a sign. These both are almost similar. So over here, this function is a scalar function. What do I mean by scalar function is this input x. This is a scalar. This is some number 2, 3, 4. This is a number. And the output is also a number. So to give you an example, say y is equal to sine theta. So the input over here in this function is theta. So the theta is a scalar value. It is a number. It can be say in degrees 45, 90. It is a scalar. And output also is a scalar. It can be anything from -1 to +1. So this is a scalar valued function. Now you can consider a vector function, say f of x, such that it is a combination of many different functions. So this capital F of x is a vector function where the first element is a function f1 of x, the second element is f2 of x. Like this, there are some m values. Also, the input that you have, this input is also no longer scalar, but it is a vector like this. So now both of these things have become a vector. So this is the same case as this. Over here you can see p0 is a vector. It will be some parameters, and your output, that is say x, is also a vector. So hence this is known as a vector valued function. So if you just see the Taylor series for a vector valued function, it is quite intuitive from this. So this we have studied in our high school, 12th standard or somewhere. So now just extending this to vector value function. So you can see that over here this was a scalar. I'm just replacing it with a vector x0. So where x0 will be some initial value of the first, initial value of the second element, like this, initial value of the nth element. Okay, and similarly del x is also some vector quantity which is telling you change in first, tweaking first parameter so that it goes towards the gradient, towards the minimum value x2, and the story like that. So this is also vector, this is also vector. Okay, so what do you get is f1. So you can just compare to this. So this is nothing but f1 of x0. So this thing comes plus del f1 x by del x1. So now because now this is a vector function, hence you will see a partial derivative over here. So since this is vector, you will see you first derivate this function f1 by the first element x1, and you multiply with del x1. Then you do that for the second element. So you will have del f1 x by del x2. So like this you keep on going on for the till the last element. So you will have del f1 x by del xn, and there will be multiplied by del xn over here. So I hope this is clear. So over here this del x is a vector consisting of del x1, del x2, del xn, like that. Okay, so this was for f1, the first function over here. Similarly, you could have an equation for the second function, similarly for the mth function. So like this you will get many equations, or in particular you will get m equations over here. Okay, so this is like trying to come from a scalar value function to a vector value function. Okay, next. So now if you just put this together, if you just try to look this together, so this whole thing that is over here, if you make a vector out of this, that will be your output, the vector output that you have. If you see this thing over here, so this thing can be written as this f. So that is our vector output for all the initial estimate. So there is x0 over here. Okay, and if you see this thing over here, so there is a del f1 x by del x1. So that you can see over here. Then there will be a del f1 x by del x2, that you will see over here, and like this you will go till del f1 x by del xn, that you will see over here. So like this you can just convert whole of this into a matrix, and this matrix is known as the Jacobian matrix. So basically when you are trying to take a derivative of a vector function, so this is a vector valued function with respect to some vector, you get a matrix. That's the simplest explanation for a Jacobian. So you see, you have to first derivate the first function f1 with x1 x2 up till xn, then you have the second function, and like this you have all the m functions. And there is this del x over here, the change, how much should I change my initial estimate. Okay, so this is what is known as the Jacobian function. So that is what we have over here. So over here f of p naught, so that is our initial estimate, plus you will have to tuke this p naught so that you go into the right direction. So this can be given as f p naught plus j del, where where j is nothing but our Jacobian matrix. Okay, so now this is our new error. So epsilon 1 is equal to some f p naught plus del. I have added some del quantity which has given me a new error, say epsilon 1. Okay, now just putting Taylor series into this, so you get epsilon 1 is equal to, just substituting this value over here, you get this thing. Now we know that epsilon 0 is nothing but f p naught minus x, right? So we can just take these two terms together and you get epsilon naught over here. So you get epsilon 1 is equal to epsilon naught plus j delta. Okay, now you can assume this small step to be linear. So over here, if this is a function, if I am say over here, let me take a pen. So if I am over here, this is my p naught, and now I want to say go into this direction, and I'm saying I'm taking a small step. So for a small step, you can assume this to be linear. So hence the name locally linear. So we are assuming that for small steps, this function is linear. So that is what we are doing over here. So hence, for a small step, now we are going to consider that this is a linear function over here. Okay, so we are going to minimize this because we want a lesser value of epsilon 1, the new error. So we are going to minimize this over del. Okay, so ideally we want it to be 0. Ideally it is better if you get this as 0. Okay, so and assuming that this is a linear equation, what we can do is just taking this epsilon naught over here, you have j delta. So j is a matrix, the Jacobian matrix. There's some delta that you want to estimate, and there is this epsilon naught, that is the error, the previous error that you know. So this can be termed as a least squares equation, because I am assuming this to be linear because it is a small local space, and this is a matrix, this is a parameter that you want to estimate, and this is known. So this can be written in the form ax is equal to b, and just by getting the least square solution, which is this, you can finally get the del. So what is the update by which you get a lesser error is this update. So just put this update over here and you will get a lesser value of the error. So that is the main motive of this. Okay, let us just see the algorithm in detail. So first what you will do is you will get an initial estimate p naught. Okay, so now with the p naught calculate the error. Okay, now calculate the Jacobian from this equation. So you know f, so by that just derivating the f with respect to the parameters at p naught, you will get j, and put it into this formula, you will get the del value, the del naught value. Now just so when this is the 0th case, so when you are calculating the first iteration, so p1, so when I is equal to 0 basically, so you'll get p0 plus del 0, you got del 0 from here, you have p0, you just add them, you'll get p1, 0 plus 1 p1, and you put that p1 over here, again get the new error, again calculate the Jacobian, put it into this, and you will get del 1. Now that is your first iteration, which is over. Then go for the second iteration, third iteration. Repeat these steps until you get convergence. And like this you can find out some parameter p which is giving you the minimum error. So this is the Gauss-Newton's method. Okay, now let us see the Newton's method. So Newton's method is some sort of generalization of the Gauss-Newton method. We'll see how. Okay, so now let us just consider a scalar valued function. Say we have a g of p, where p is a parameter matrix that we saw earlier, the same parameter vector, I'm sorry, not matrix, parameter vector. And you have some function g which is on p, which is taking the input p, and this function you have to minimize. So you have to see which is the p, the parameters which minimize this function g. Okay, so again applying Taylor series, you have some initial estimate p naught, and you want to tweak that estimate so that you go into the right direction. Okay, so again applying Taylor series, so this is the simple Taylor series. So you have g of p naught plus del g by del p. So now since p is a vector, hence there is this partial derivative notation, and you have del multiplied by del. Now we are also going to consider the second term, that is your square term. That is also what we are going to consider. And if you see over here, this thing is known as a Hessian. So just to give you a brief, so if you have a scalar function, so here g is a scalar function that gives an output a scalar. It has an input a vector, but it gives output as a scalar. So hence this is a scalar function. So you have a scalar function. When you derivate the scalar with a vector, so g of p naught is a scalar quantity. It will give you number 1, 2, 3, some number. If you derivate this with a vector, so since p is a vector, hence you are derivating del g by del p, you get a vector quantity which is known as a gradient. Derivating a vector with a scalar, you get a vector quantity. Now over here you'll see that del g by del p is a vector quantity. So derivating, or the second derivative of g, which is derivative of this thing, so derivating a vector with respect to vector will give you a matrix which is known as an Hessian matrix. So this thing over here is nothing but the Hessian matrix. Okay. Okay, so this is the Taylor series that we have, and now we have to minimize this function. So that is del g by del dg by d del is equal to 0, because we have to minimize this. That means just take the derivative of this this scalar value function and equate it to 0, because that is our minimizing rule. If you want to minimize, just take the derivative, equate it to 0. So when you do that, what will happen is this term will go, because you are derivating with respect to del. So this term will go. In this term there is only this del quantity over here, so you will only be left with this. Quite intuitive. So this is represented as gp. So I'm just going with the notation of the book. So this is gp, this thing over here. You can see that over here. And if you just take derivative of this quantity, you get g. So this quantity, so this thing Hessian is denoted by gpp. And since so this you can take it as a square, so del transpose, and there is a del over here, so this is actually a del square. So that turns out to be 2 times del. So hence there is 2 times and a del sitting over here, so the 2 and this 2 get cancelled, so you get this equation over here. So where gp is the gradient and gpp is the Hessian. Okay, and now just taking this gp the other side, you get gpp del is equal to minus gp. Okay, now this is your main equation. If you solve this equation, you know gpp, you know the gradient, you know the Hessian, you can find out what is the optimal del which will minimize this function or minimize the error. So why did I define a scalar function? Because we can always have the cost which is a scalar function. So again we are going to solve the same equation, say x is equal to fp, the same equation we are going to solve, just the difference over here is now I am going to consider this cost. So one can have a norm cost. So we have seen the same cost in least squares. We took a half like this, where this is the error quantity. So this is a new notation. So that is del of p. That means the error produced by this p parameter vector. So hence del of p, epsilon of p. So epsilon of p is the error. I'm just trying to minimize the norm of this error. So this becomes my scalar function over here, because input is a vector, this p is a vector, and output I'm just taking a norm, so I'm getting a scalar quantity, a number. So now this can be written like this, simple linear algebra thing. Okay, so this is the same thing that was in the previous slide. So now you can calculate the gradient. What is the gradient? Gradient is nothing but you derivate this thing, or for that matter this thing, with respect to p. So that will be your gradient, because p is unknown. You want to know what is your parameter, right? So p is unknown, so you just take the derivative of this thing with respect to p, that will be your gradient. So you can see that the gradient will be this. Why? Because so one can assume this to be some square. So actually this is a square. So in normal scalar terms this is square. So the derivative of this will be 2 times the same thing. So if it is say half x square, so it is 2x. So 2 times this same thing. So hence you will see that the 2 cancels out and you get the same thing over here. So this same thing is this thing, del. And now since this is a function of p, so you will again have to derivate this function with respect to p by the chain rule basically. So that is over here. So this del p notation that you see is nothing but del of epsilon p. I'm saying this as del sometimes, so please ignore that. This is epsilon. So del epsilon p by del p is this notation, epsilon p. Okay, so intuitively this is the gradient of this function if you derive with respect to this p vector. Okay, and Hessian, if you just take the Hessian is quite simple. Now you again have to derivate this thing with respect to p. Okay, so this is like a uv rule. So first take the derivative of this thing, or first leave this as it is and take the derivative of this thing. So just leaving this as it is, taking derivative of this thing, you will get a p down. Okay, then plus leave this as it is and take this derivative. So the simple uv rule that we have in our simple scalar derivative, so that is the same thing. So by this you can calculate the Hessian and you can calculate the gradient. Okay, so now we have all the pieces. Now let us see the algorithm. So the algorithm is such, again you are having a initial estimate p naught, put that estimate, check out the error. Okay, now calculate the gradient by this formula, calculate the Hessian by this formula. You know that this equation will give you the reduced error. So now calculate del, solve this equation. You have the error, you have the gradient, you have the Hessian, solve this equation and you will get the first iteration del naught. Put that over here, calculate new p1, put that again into the equation, calculate new gradient, new Hessian, again you will get this, calculate the del and repeat this till you converge. So quite simple algorithm. It looks to be simple, but actually calculating Hessian is a difficult task. So this can be complex calculation. So yeah, but this is the Newton's method algorithm. Right, so now that we have seen the Newton's method and the Gauss-Newton's method, a gradient descent is a very small fix to the Newton's method algorithm. So if you see, as I just said, that calculating the Hessian is little difficult. So what one can do is just ignore the Hessian. We will not calculate the Hessian over here. So you'll see that the algorithm is almost the same. You'll have an initial estimate P naught. Put into this, you'll get the first error. Now calculate the gradient. So this is something that you will have to do. Now instead of calculating the Hessian, what I am saying is, now the Hessian is some lambda times I. So I am going to decide the Hessian, and that is going to be a parameter, that is lambda. So this is something that the user will have to define. So this controls the length of the step. So as I was saying in my this case over here, so this step size as to how much should I jump. So this step size is calculated by lambda, this step size, how much to jump in one iteration. So actually the Hessian was telling you how much to jump, how much will be an optimal jump. But since calculation of Hessian is a tedious job, what one can do is one can decide beforehand how much should we jump. So that is the quick fix that gradient descent algorithm has done. And now the same thing is done. So it is quite similar to the this method, Newton's method. Just the difference is the Hessian is not to be calculated now. And you repeat this till convergence. So that is the simple gradient descent algorithm that we have. Now let us just compare these three. So if you see, the only difference actually in all the three algorithms is this update equation. In the first, that is the Gauss-Newton method, we use the Jacobians. So to calculate Jacobians is also a difficult task. So that is something that you can do. Or else if you see the Newton method, there you will have to calculate this Hessian. So this is an even difficult task. So so Newton method actually assumes this to be a quadratic estimate. So as Gauss-Newton assumes a linear estimate, this assumes a quadratic estimate. That's only difference, because we are also taking the second derivative or the Hessians. So this is like a quadratic assumption. And the gradient descent is quite simple. No Jacobian, no Hessians, just a lambda, a scalar value, which you will have to decide, and that will give you your next step. So the problem with gradient descent is only to estimate. How can one estimate the lambda? So what will happen is, if your lambda is very big, it will try to oscillate, because it will skip the it is highly possible that it skips the minimum point and goes at the other side. Then again it will have to come back. So like this it can oscillate if lambda is very big, and if lambda is very small, then it will take time to converge. You'll have to increase the number of steps, so it will take a lot of time. So that is the only problem with gradient descent, but otherwise it is a very simple algorithm. So there are a lot of comparisons given in the book Multiple View Geometry in Computer Vision. So you can just refer to this section, Appendix 6, where you will see the different comparisons and some more details about the three algorithms. So that's all for this video. Thank you so much for watching. Thank you.